Hello class and welcome to Chemistry in the Physical Setting. We're going to begin with Unit 1, Atomic Concepts, and Lesson 1, Atomic Theories. And our major understanding for today is that the modern model of the atom has evolved over a long period of time through the work of many scientists. Okay, and we'll begin with Dalton's atomic theory, which was developed in 1808. And there are four main points to Dalton's atomic theory. The first being that elements are made of small particles called atoms. And so these atoms make up all matter, and Dalton visualized these as solid spheres. So the model became known as the hard sphere model. And these atoms were the smallest unit of matter, and so because of that, they were indivisible, which means they could not be separated into smaller components of matter, that the smallest individual component of matter was an atom. Okay, so atoms cannot be, according to Dalton, created, destroyed, or subdivided, broken down into smaller portions. The third aspect of Dalton's atomic theory is that atoms of a given element are identical in both size and in mass. And so if we look at two examples, helium and neon, we'll find that helium atoms are all the same size and exact same mass. But if we were to compare the atoms of helium to the atoms of neon, we would notice that the atoms of neon would be greater in mass and have a different size. And so the only thing that differentiates elements from each other are their size and their mass. Also, that atoms of different elements can combine to form compounds. So an example would be if we considered hydrogen and oxygen combining to form the compound water. So the element hydrogen is composed of small atoms that are identical in size and in mass. And oxygen is a different element, so its atoms have a different size and hence a different mass. And these atoms will combine to form water, which is one oxygen for every two atoms of hydrogen. Okay, and this leads us to our final point, which is that in chemical reactions, atoms are combined, separated, and rearranged. And we'll continue to look at water as an example of this. So we have hydrogen gas combining with oxygen gas to form the compound water. And in order for this to occur, we're going to need two molecules of hydrogen gas, which each consist of two atoms of hydrogen. And so this is called a diatomic molecule because it consists of two of the same type of atom. And oxygen, we need only one molecule of oxygen, which again is also diatomic, so two atoms of the same element. And what's going to happen are these molecules are going to separate, and these atoms are then going to rearrange themselves to form the compound water, which consists of one atom of oxygen and two atoms of hydrogen. And this proportion is fixed, which means it cannot change. If you have a molecule of water, it has to have only one atom of oxygen and two atoms of hydrogen. And if it has a different proportion, then it can't be water. So this leads us to J.J. Thomson's cathode ray experiment, which began many years later in 1897. And what Thomson did is he placed two pieces of metal at opposite sides of an evacuated tube and connected both pieces of the metal to a battery. So basically what an evacuated tube is it's this tube that has had all air removed from it. So there's nothing inside the tube except these two pieces of metal. And so what Thomson observed is that a ray traveled from the negative piece of the metal to the positive piece of the metal, and that the ray was attracted to the positive end of a magnet. So from these observations, J.J. Thomson was able to conclude several things about the atom. The first and most important being that the atom is no longer this small hard sphere that is the smallest unit of mass. there's actually something smaller than the atom that makes up the atom, and that being that atoms contain small negatively charged particles called electrons. And Thomson believed that these electrons were uniformly distributed throughout the mass of the atom. And this became known as the plum pudding model because the model resembles plum pudding, or you could think of it as like a chocolate chip cookie where the electrons are the chocolate chips. Now, because electrons are negatively charged, there must be something positive to cancel out that charge. So Thomson believed that the electrons are embedded in positive matter, again, uniformly distributed throughout the atom. Okay, and so this became known as the plum pudding model, where you have these negative electrons embedded in this positive mass. So shortly after J.J. Thomson, Ernest Rutherford began his experiments with gold foil and alpha particles in 1908. And so what he did is he bombarded a thin piece of gold foil with alpha particles, which are just small positively charged particles. And so what he found is that most of these alpha particles went straight through the foil. But some of the alpha particles were deflected. And so he was able to observe that the alpha particles went off in a completely different direction. In fact, some were observed to come straight back towards the alpha beam. So Ernest Rutherford concluded several things about the structure of the atom from his gold foil experiment. One being that atoms are made up of mostly empty space. Since most of the alpha particles went through undeflected, the assumption was that there was nothing there. So atoms are mostly empty space. But at the center of the atom is a dense positive center called the nucleus. And he was able to come to this conclusion because, again, most of the alpha particles went straight through the gold foil undeflected, which means they didn't collide with anything. Nothing must be there. But some alpha particles were deflected, which means they didn't go straight through. Some actually came straight back. And since alpha particles are positively charged, his assumption was that whatever it was that they collided with had to have had a positive charge also. So this electrostatic repulsion deflected the alpha particle back in the opposite direction. In 1913, Niels Bohr developed his planetary model of the atom, and the way Bohr did this is he placed samples of elements near an energy source, and he found that atoms absorbed energy but released a specific or discrete amount of energy in the form of light, and he called this the bright line spectrum. So if we were to look at two examples, lithium and hydrogen, okay? So he placed samples of both of these elements within a flame or electrical current, and what he would find is that both elements gave off different forms of light. And when viewing this light through a spectroscope, he found that each element gave off specific bands of light that were individual to that element. So for instance, lithium has this very dark red spectrum, and that's what gives it its red color, and which is right here. And hydrogen has this red band, but also has a very low purple band, and that's what gives it this kind of like reddish purple or reddish pink color. Okay. So conclusions from the atomic spectra. So electrons can occupy specific distances or energy levels around a nucleus. So if we were to look at an atom, we have the nucleus in the center, and then we have an electron, and the electron can orbit only around a specific energy level. Think of this as like rungs on a ladder. It can only be at these specific positions that are at certain energy distance from the nucleus. Okay. So when an electron absorbs energy, they move to a higher energy level. So energy going into this electron will move it to the higher energy level. But the electron cannot stop anywhere in between these two energy levels. It is immediately promoted to this next energy level, and this is called the excited state. Okay? And so excited state electrons are unstable, and since they're unstable, they quickly return to the lowest available energy position, which would be the ground state. And to do this, they have to release energy, and they release energy in the form of light, which is what Niels Bohr observed with the bright line spectra. Okay, so if we have an electron that is in the excited state right here, and it's unstable, so it's going to fall back down to the ground state, and it's going to then release energy in the form of light. Okay, and so the reason why this is called the planetary model is because it was determined by Bohr that electrons orbit the nucleus at specific distances similar to the way that planets orbit around the sun. Okay, Bohr's model was able to explain small atoms, but when we started to consider larger atoms, the idea of electrons orbiting in circular paths around a nucleus didn't seem to make much sense. And so this modern or wave mechanical model became accepted. And in the modern or wave mechanical model, basically all of the experiments that we've previously talked about and others led to the development of this modern atomic model. And so in the modern atomic model, we still have a positive nucleus, and it's surrounded by not orbiting electrons, but orbitals. And these orbitals we like to think of as regions of most probable location of an electron. So they're not indefinite, they're more of like a cloud. So an electron could, but it's a high probability that electron is within this region of space. So it's possible for an electron to be outside the region of space, but it's a very low probability. Okay, so there's no definite lines to the positions of these electrons, but these are the general areas in which an electron would exist. And this is the current model of the atom. And so that's many of the atomic theories that led to our current modern or wave mechanical model. And so that's the end of the lesson, and I'll see you tomorrow in class.